Welcome back. In our last video, we introduced probability distributions and random variables. And we went through a couple examples, including for this one, which is the Calc 1 grades, the distribution of grades in Calculus 1 at IU Bloomington for a particular professor. And so I want to talk a little bit more about this in detail, starting with how to describe a distribution. Right, the three main features were that you had to hit on the shape of the distribution, its center, and its spread. So for shape, you could say that it's unimodal and symmetric perhaps, or maybe it's skewed left or right, are there outliers, that kind of stuff. And I know outliers was kind of its own thing over here, but I'm going to put it under shape because what you used for center and spread depended on the shape. If you had a unimodal and symmetric distribution, you use the mean as the measure of center and the standard deviation as the measure of spread because they utilize all the data values. And if the shape is unimodal and symmetric or normal-ish in shape, then you have no issues using these, and they're better because they use all the data values in their calculation. If instead you have a distribution that was skewed left or right, or maybe had some outliers, or both, you don't want to use the mean and standard deviation because those values tend to be greatly affected by either skewness or outliers. So instead, we use more robust or resistant statistics, the median for center and the IQR for spread. They don't use all the data values, but they ensure against these inflating their value. So, in general, that is how we used to describe a distribution. But if we are instead describing the probability distribution of a random variable like this, we still want to describe the shape, center, and spread. But for center and spread, we're going to want to stick to the mean and standard deviation, even if the shape isn't necessarily unimodal and symmetric. So a little additional notation for you. When we're dealing with these probability distributions, again, we want to stick to the mean and standard deviation for center and spread. And this is how they're notated. The mean of the random variable x is going to be denoted mu x, right? We already knew that mu represented the population mean. So since this represents the population, we're going to call it mu. And since the random variable is x, we call it mu x. That way, in case we ever have more than one random variable, say x and y, we can differentiate between the mean of x and the mean of y. That would be mu y. The mean of a random variable is also called the expected value, and the expected value of x is denoted e of x. So these are interchangeable. They both mean the same thing. They're just the average of the distribution, and we'll get to calculating that in just a second. The standard deviation for the random variable is sigma x. Again, this is the population parameter sigma for standard deviation for the variable x. In introducing this notation here, I mentioned the fact that these are parameters because they're describing a population of the distribution for a random variable. And so I want to highlight the difference between the notation for population parameters versus sample statistics. Okay, these are what we dealt with in prior units, like if we took a sample from a population and we want the mean and standard deviation of the sample, that has its own notation. If we're talking about one of these, the population distribution of a random variable, we're going to be using the notation for population parameters because we're describing an entire population. So the mean is going to be mu x. Okay. Also, it could be e of x if it's asking for an expected value. But again, these are the same. And the standard deviation, sigma x. Notice the population parameters get Greek letters, right? If you can find some way to attach Greek letters to population parameters, that's going to be helpful because the sample statistic notation doesn't involve Greek letters. the sample statistic, so if you take a sample, the sample mean is just x bar. And the sample standard deviation is Sx. Okay. And it might seem simple enough to keep these separate right now, but the longer we go in the course, this difference seems to kind of disappear for some people. Maybe they forget which notation is which, or maybe they don't even know whether they're talking about a sample mean or a population mean. I want you to know right now, those are two very different things. They're calculated the same way, whether it's a population or a sample, at least for the means. But it's important the notation you use. Because if you use x bar to talk about a population, you can do everything else right, and you won't get full points on a free response question. It is important for you to keep it straight. So anytime we calculate a mean or a standard deviation for either a population or sample, make sure you pay attention to the notation you use and that it's consistent with the context of what you're dealing with. In these examples, we're talking about populations. All right, so I think we're finally ready. Let's calculate the mean GPA score for all Calc 1 students at IU Bloomington. And we're going to be using this table here, which represents the distribution of all the calculus students in that professor's class. And we're going to treat that as the population here. So if we want to calculate the mean of the population, we're going to start right off by making sure we use the right notation. This is a population mean, so mu of x. And the formula for how this mean is calculated, we're going to take each of the xi values here, so the 0, 1, 2, 3, or 4. Leave a little space here if you're writing your notes along with me. We're going to take all those xi values and we're going to multiply them by their corresponding probabilities. Okay, so this is another reason we introduced the xi notation here, because in the formula, that's how it's looking. So we're going to take those, we're going to multiply. So we're going to get a product for each of these. We're going to do this times this, this times this, this times this, this times this, and this times this. We're going to add up all those products over all of the xi values. Okay. So I want you to know that this formula here, the formula for the mean of a probability distribution, is only for discrete probability distributions, right? When you write this formula, you're assuming that there are a finite number of these xi values. If you have a continuous probability distribution, you would have infinitely many terms here, and that's going to be really hard to add up. Okay, so this is only if you have a discrete probability distribution is when you're going to use this formula. So let's take it for a spin, shall we? Let's actually take all the xi values times their probabilities. So this is going to be 0 times 0.047 plus 1 times 0.163 plus 2 times 0.279 plus 3 times 0.30. Is that a 2? Yes. Sorry, that kind of looks like a 7 of mine. This is a 2. 3 times 0.302 plus 4 times 0.209. And we get 2.46. Not a super stellar GPA, but, I mean, it's Calc 1. Lots of non-math majors at IU Bloomington, I imagine, are taking Calc 1, so it's not necessarily their forte. Seems reasonable. Calculating this value is one thing. Being able to interpret what it means is another important thing. So what does this mean? How would you interpret that value? Well, let's take our language here and just copy it. The mean GPA score. Mean GPA score for all Calc 1 students at IU Bloomington is 2.46. Perfectly coherent sentence. All I did was copy this down, essentially, and then put the number at the end. Super easy, right? So, if you're given a probability distribution like this, that is how you calculate the mean. Just take each of these products, add them up. Simple enough. Now that we know how to calculate the mean for a discrete probability distribution, let's see if we can calculate the standard deviation for all the GPA scores for the Calc 1 students at IU Bloomington and interpret the value in context. I remembered to write it this time. So, we're going to have to start with a formula for the standard deviation of a discrete probability distribution. Okay. Again, this is for a population standard deviation, so you've got sigma x. And the formula for the standard deviation is going to be similar for the formula that we used for a sample standard deviation. And that is, we're going to take each individual value of the random variable, so the GPA scores along the top here, and we're going to subtract out the mean that we already just calculated. We're going to take that difference for each of those xi values and square it. This should be looking pretty familiar from previous standard deviation formulas. This is where it's different though. For a discrete probability distribution, we're going to have to incorporate these probabilities. We multiply those squared differences times the probability of that xi value. We add all those up across all the xi values. The formula as it's written would give us the variance, but we want the standard deviation, so we take the square root at the end. Maybe. It's a little bit of a honker of a formula there, but that's what it is. So there is a square root sign there. These two formulas for the mean and the standard deviation for a discrete probability distribution will be included on the AP test formula sheet. And I will make sure that you have access to a digital version of that for any quiz or test going forward. I'll probably just put a link in Canvas for the formula sheet so you have access to that. You do not need to memorize the formulas themselves, but you do need to be able to apply them to the correct situations and use them correctly. So let's go ahead and use that formula to find the standard deviation for this variable. All right. We're just plugging and chugging here. So we're going to need the square root of a whole lot of stuff. We're going to start with the first value of xi, which is 0, minus the mean. Now, this term is going to be the same for all the different xi's because there's only one mean. It's 2.46. We're going to square it and then multiply by the probability of getting 0, which is 0.047. I desperately wish I had more room here. We're going to try and fit another term in here. We go to the next xi value, which is 1. We subtract the same mean, square it, and multiply by the probability of getting a 1, which is 0.163. Okay. I'm I'm continuing on the next line here with my ellipses. This is still a square root sign. And I'm actually going to skip over the next two terms, which would be 2 minus 2.56 squared times 0.279 plus 3 minus 2.46 squared times 0.302. And I'm going to go ahead and skip to the last term, which would be the last xi value, 4, minus the mean, 2.46, squared times the probability of getting a 4, which is 0.209. So this is one of those things where if you're watching on like 2 times speed, not even listening to what I'm saying, and you don't know what's going on here, ask me in class. All right? I'm just too lazy to write it all. So we need to calculate that very carefully. I would not, I'll repeat that, I would not recommend that you type all of this into your calculator at once. That is a recipe for getting the wrong answer. So, even if you write all this down correctly, which I would if I were you, at least write it down with like the first term and the last term, with the dots in the middle. That shows that you have the right idea of setting it up. But what I would do is, I would type in 0 minus 2.46 squared, enter, times 0.047, enter, and write that down. Do 1 minus 2.46 squared times 0.163, write that down. Do that for every term. You'll have 5 terms in there. Add them all up. Then take the square root at the end. Okay? If you think you're special and that you can type all this without making a mistake, ooh boy, you're playing with fire. I would not do that. Okay? If you know you've set it up correctly, make sure you get full credit by getting the right answer, by being careful with your calculations. There is no reward for going fast, but there is a reward for getting it right. So be careful when you calculate these things. If you go ahead and do that correctly, that could be a good exercise to make sure you know how to do it right. I get 1.13, approximately. 1.13. So, again, we need to interpret that value in context. It's a little trickier interpreting the standard deviation of a distribution than it is the mean. Remember, our interpretation of a standard deviation is that it's the average distance that an individual is from the mean. So this is what that looks like. So here is the interpretation I came up with. GPA scores for Calc 1 students at IU Bloomington typically vary by about 1.13 from the mean of 2.46. You don't have to phrase it exactly that way. The important bits are the context, right? You have to state what the variable is, and that's essentially everything from GPA all the way up to Bloomington. Okay, that's all just what the variable represents. The fact that it typically varies by about 1.13 from the mean. Okay? You don't necessarily have to state what the mean is. I think it's helpful. It makes things more clear. And in most contexts, your variable is going to have units. It just so happens that GPA scores don't have any units, so we didn't have to put any here. But for most variables, like if you're talking about height of people, you're going to want to make sure that your interpretations include the units, whether it's inches or centimeters or whatever the units are for your variable. Make sure you include that. That's part of the context that you need. So I think what we've covered so far could be a free response question on an AP test, I suppose. It could be, hey, here's your distribution. This wouldn't be there, obviously. Part A, calculate the mean and interpret it. Part B, calculate the standard deviation and interpret it. Part C, describe the distribution. Oh boy, are we ready? I think we've got everything we need. Make sure you hit all the points you need to. I'm guessing most people aren't going to pause the video right now and write their own description, although I think that would be super helpful. If you do that, fantastic. If you don't, well, I hope that's good enough for you. You need to get practice at some point. let's show you what we got. This response deserves multiple sentences. This is what I have. Calculus 1 scores for IU Bloomington students appear to be left skewed, with most students earning a 2 or higher. The average GPA score for these students in Calc 1 is about 2.46, and scores typically vary from this mean by about 1.13. Now, I said this could be a free response question with parts A, B, and C. There's no way they would ask you to interpret the mean for part A, interpret the standard deviation for part B, and then ask you to describe the distribution, including describing these two things in part C. But I want you to see how the interpretations for the mean and standard deviation fit their way into describe this distribution. Okay? If it helps, once you calculate an individual parameter or statistic for a sample, interpret it. That way, if you're asked to do something holistic for the distribution, you've got each of the pieces, and it's easy to just plug them in where they go. So, I want to highlight why this hits all of the things it needs to. And for those of you that watch my videos religiously, you know that I've stopped using colors. It's all black, because colors wreak havoc with the paint on my wall here, and I am going to use colors here because it's important and I feel like it's helpful, so I hope you appreciate this. We need to talk about the shape in our response, and that happens here when we call the distribution left skewed. Remember, what that means is that if we were to see a histogram, it would mean that the tail is longer on the left side. Now, I don't remember if we made a histogram for this or not. We may not have. But we essentially have the histogram right here. These would be the numbers on the horizontal axis, and the probabilities would be how tall the bars are. So the bigger the number is, the taller the bar. This is going to have the tallest bar. This is going to be lower, but still not super low. But you can see those numbers really start leveling off and going down as you go to the left. This is the longer tail, so that's where the left skewness comes in. And maybe that would be enough to hit the shape, is to call it left skewed, but I provide a little bit more, saying specifically where that skew is. Most students earn a 2 or higher. I could have said in the same way, there are very few students scoring less than 2, let's say. I could add something there. That's not particularly necessary, but you would need to say something about it being symmetric or skewed or whatever. Okay, so that's shape. Center. Okay, we talked about the average GPA score being about 2.46. Cool. The spread. We have scores typically varying from the mean by about 1.13. If I underlined all this, all the Y's and P's would really ruin this marker. So just know that the spread is really everything in this clause. Shape, center, spread. One more marker. What else is important to put in this description? Context. I took out on purpose describe the distribution in context just to see if you remember that that's something you have to do. If you just said something like the distribution is left skewed with an average of 2.46 and a standard deviation of 1.13, that would not get full credit. Everything I just said is correct, but it lacks context. You need to link these numbers and the shape to what the variable is. Calculus 1 scores. And really, this whole phrase is context. Average GPA score for these students in Calc 1. Scores. Okay? Now, when I graded a free response question for the AP test last year, the way they graded it was you had to include all of these pieces correctly to get full credit. But if you had these three without context, you only got a P. But to get credit for context, you only had to include once what the variable was. So if I had just said Calculus 1 scores for IE Bloomington students, blah, 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 and left out the context here and here, that would still get full credit. However, I feel like including the context for each of these things helps tell a more cohesive story. It would be awkward to include context here but not here, in my opinion. Okay? Maybe the stronger you are at English, the more natural it is to just include the context throughout, but make sure you at least put it somewhere. What is the variable that you're discussing? That's important to put in. So this response would earn an E. I would say usually the way it's graded, if you have all four of these things and they're correct, it's an E. You need at least 3 of the 4 to get a P. And if you have less than 3, it's an I. You might as well have not even written anything. Okay, so the fact that you can get 3 out of 4 is a P means you can leave out context, you could leave out shape by itself, you could leave out the spread by itself, and still get some credit. But you need probably at least 3 of those to get something. So I think, yeah, that's all I wanted to cover in this video. Hopefully, after I edit it down, it's not too long. But we learned a lot in this video. We took this probability distribution, we learned how to calculate the mean and standard deviation of it, and we went through how to describe the distribution again, which is something we've talked about in the past, but now we can apply it to this. Specifically for these formulas, it's important you know they're only for discrete probability distributions. They won't make sense for what we will be talking about later, and you need to know how to use them, but you don't have to memorize them. They're on the formula sheet. So, in our next video, we're going to talk about, what are we going to talk about? Oh, we're going to go through another example like this, and then we're going to talk about what happens when we mess with this random variable. We can add to it, we can multiply or divide, we could talk about multiple variables at the same time. There's a lot to get to with these probability distributions. We're going to be in chapter 15 for a while longer, so there won't be any homework due for a while. There won't be a quiz or a progress check for a little bit, but this is an important piece of the unit, and I hope that you can stay with me until the next video, and we'll see you then.